Hello, everyone. In this talk, I'm going to present CosTLO, a system we designed to reduce tail latency of using cloud storage services. And this is a joint work with Curtis and our advisor, Harsha. So I want to start my talk by making clear about what a setting is. So when I say cloud storage services, I mean those services like Amazon S3 and Windows Azure Storage, which provide application developers with convenient and high-performance object storage. So application and their users can simply issue, put, and get requests to store and retrieve data in those services. And in particular, our interest in those services because they have many data centers across the globe. If we consider a popular application that has users all over the world, by leveraging the geo-distributed cloud data centers, every user can be served by the closest data center and have low latency. For example, based on our measurements, more than 90% of Platinum nodes can fetch small objects within 100 milliseconds from their closest data centers, from their closest S3 data centers. But this low medium latency is not what you always get, because we found that cloud storage services also have very high latency variance. Therefore, to quantify this latency variance as well as its impact, we conducted a one-week-long measurements from 120 Platinum nodes to their closest S3 and Azure data center. Each Platinum node was uploading and downloading a 1 kilobyte object every 3 seconds. And the graph here shows the latency we observed at the median Platinum node. So the red bar on the graph is the median latency, and the blue bar on the graph is the 99th percentile latency. And there are 3 takeaways from this graph. First, for GET requests, in both clouds, the 99th percentile latency is at least 70 milliseconds higher than the median latency. And second, for PUT requests in both clouds, the 99th percentile latency is at least 200 milliseconds higher than the median latency. And third, the relative latency inflation is at least 2x. So this graph shows that even though the median latency is low, there are still a small portion of requests that are suffer from high tail latency. But why this high tail latency is bad? In fact, there are many scenarios that high tail latency can cause application performance degradation even in the medium case. For example, when a user is downloading a web page, the user request to the browser can cause the browser to issue many storage requests to fetch the object on the web page. Or in the social network application, the user's update can cause his or her friends to fetch that update. And in both examples, one user-level request requires application to issue multiple storage requests, and the user-perceived latency is limited by the slowest response. And here's the experiment we did to further quantify the impact of high tail latency in the web page example. So we used Platinum nodes to download a web page containing 50 objects. And what we observed is that the median web page downloading time doubles the latency in the ideal case. So the ideal case here, I mean when there is no latency variance. And the 99th percentile latency is even 20 times worse than the latency in the ideal case. So this shows that if we want to improve the median application performance, not only we need to have a low medium latency of single requests, it is also very important to reduce the single request, to reduce the tail latency of single requests. So now, hopefully you will agree with me that high tail latency is a problem. But how can we reduce high tail latency? So in fact, we're not the first to look at the tail latency problems. There has been a lot of recent work reduce latency variance by designing new data center network, new storage services, new storage systems, new request scheduling, and resource allocation policies, including many talks we have listened during the past 2.5 days in this year's conference. So all of these systems are doing a good job reducing latency variance. But in order for application to really benefit from them, the cloud providers will have to first modify their underlying systems. And right now, it is still unclear when and if the cloud provider will do so. Therefore, our consideration is, what can application providers do to reduce latency variance without relying on cloud providers? So next, let me tell you how do we do this. So our main observation from our measurements is that tail latencies are dominated by isolated latency spikes. So any approach that reacts after seeing latency spikes will not work very well. Therefore, our approach is to proactively augment storage requests with a set of redundant requests so that the earliest response can be considered. But how exactly can we use redundancy? So let's consider a client want to fetch object in the storage service. So the simplest way to use redundancy is just to issue redundant requests to that object. And this simplest approach can offer some benefits because the redundant requests may take different internet paths, or may take different data center network paths, or may be served by different replicas inside the storage services. Note that the replicas are created by storage services for load balancing and fault tolerance purpose, but here we can leverage it to avoid slow replica. But this simplest approach has 4 issues. First, it is not guaranteed that requests may hit different replicas. It is possible that requests may be served by the same slow replica. And second, this approach requires multiple copies of data transferred out of data centers, which will incur high data transfer costs. Furthermore, some of the requests may take the same slow internet paths or same slow data center network paths, which will incur high network latency. So next, let me talk about how to address some of these issues. First, let's look at the issue of requests hitting the same replica. So our idea to avoid a request hitting the same replica is to explicitly create multiple copies of objects inside the storage systems and using different copies to serve different requests. So now we're guaranteed that different requests will hit different replicas. And here is the experiment we did to show the effectiveness of this approach. So we set VMs in cloud data centers, and we issue requests to the same copy and different copies of objects in the local storage services. And the graph here shows the latency observed at the S3 US West region. The red bar is the 99th percentile latency of single request, and the yellow bar is the median latency of single request. As we can see, there's a big gap between the 99th percentile latency and the median latency. So if we issue 2 requests to the same copy of objects, the blue bar is what the 99th percentile latency looks like. So as we can see, using multiple requests to the same copy of objects does help reduce tail latency. But there's still a big gap between the 99th percentile latency and the median latency. Instead, if we issue 2 requests to different copies of objects, the green bar is what the 99th percentile latency looks like. As we can see, using multiple copies can greatly reduce tail latency, and it is also much close to the single request median latency. So let's go back to the baseline approach. Next, I'm going to talk about how to reduce high internet latency. So to increase the path diversity from client to data, not only we can create multiple copies of data inside the same data center, but also cross data centers. So now a client can issue redundant requests to multiple data centers and only waits for the first response. And to show the effectiveness of this approach, we did following experiments. So we use PlanLab nodes to issue requests to the closest and the second closest data center. And the graph here shows the 99th percentile latency we observed at the median PlanLab nodes. The red bar is when PlanLab nodes issue single request to the closest S3 data center, and the blue bar is when PlanLab nodes issue 1 request each to the closest and the second closest S3 data center. From the graph, we can see that using the second data center in S3 only offers slight improvements. And if we further compare this with issue 2 requests to the closest S3 data center, we can see that using the second data center in the same cloud actually does not help much. And this is because cloud providers tend to build minimum number of data centers with widest coverage. So 2 data centers in the same cloud are usually distant. And it's hard for clients to really benefit from using the second data center. But if we can combine clouds, now clients may have more than 1 closed data center to use. So let's go back to the experiment. So the yellow bar here shows when PlanLab nodes issue 1 request to their closest S3 data center and the 1 request to the second closest data center across all S3 and Azure data centers. As we can see, using multiple data clouds enable us to further reduce tail latency. So now I have told you some forms of redundancy that can help reduce tail latency. And there are some other forms of redundancy that can help reduce cost. For example, we can use relay VM to reduce data transfer cost. We can set up a timeout for issuing redundant requests. We can even use redundancy probabilistically. And the application can choose to combine some or all of these redundancies to meet application requirements. For example, application can choose using multiple data centers and using single copy in one data center and using multiple copies in another data centers. And the different combinations of these forms of redundancy will have different implications on reducing tail latency, as well as have different implications on cost. So ideally, we want to find the configuration that can satisfy application requirements with only minimum additional cost. But this is hard because application can arbitrarily combine different forms of redundancy, which will give this huge configuration space. Furthermore, application can also vary the number of redundant requests, which even make this configuration space unbounded. So the biggest challenge is, given this unbounded set of configurations, how can we pick the configuration to satisfy the application's goal with low additional cost? And to solve this challenge, we designed CosTLO. It stands for Cost-Effective Tail Latency Optimizer, and you can consider CosTLO as a middleware that sits in between clients and the storage services. And when end users or a VM in cloud wants to issue storage request, it can issue a single request to CosTLO, and CosTLO will issue redundant requests to fulfill client requests. But how does CosTLO know how to issue redundant requests? There is the central configuration selector that finds configuration for each client. And the conf selector will take 4 types of inputs. 2 static inputs, application service level objective and the cloud pricing, and 2 dynamic inputs, the application workload and the cloud storage measurements. And then the conf selector will combine all these informations and find the cost-effective configuration for each client. But in order for this architecture to work, there are several challenges. First, like I mentioned earlier, how do we search this unbounded configuration space to find the cost-effective configuration? And second, how to estimate latency distribution for any configuration? And this is very important because given a configuration, CosTLO needs to know whether this configuration can satisfy SLO or not. But not only costly, but also impossible that CosTLO needs to measure the latency distribution for any configuration. Therefore, in order for CosTLO to work, it is critical that CosTLO is able to estimate rather than measure the latency distribution for any particular configuration. And data consistency is another challenge, because now multiple copies of data may be used by the applications, so how can CosTLO guarantee good data consistency despite concurrent inputs? And due to limited time, next, let me give you an intuition for one of the challenges, latency estimation. So like I said, latency estimation is very important for CosTLO to work. And first, let's consider the simplest way to estimate latency. So giving a latency distribution of single request, we can simply sample the individual request independently and take the mean across concurrent requests. But we found that this independent sampling method does not work very well. So the graph here shows 2 latency distributions of 8 concurrent requests to the same copy of objects from a local VM in one of the S3 data centers. The blue line is the measured latency distribution, and the red line is the estimated latency distribution using the independent sampling method. So the x-axis on the graph is the latency, and the y-axis is the CCDF of latency samples. Because it's a CCDF graph, the 0.5 point on the y-axis indicates the median latency, and the 0.01 point on the y-axis indicates the 99th percentile latency. As we can see, independent sampling can greatly underestimate latencies, especially in the 99th percentile. But why independent sampling doesn't work? So to find out, we did following experiments. So we set up VMs in cloud data centers, and we issue 2 concurrent requests to the same copy of objects in the local storage service. And the graph here shows the scatter plot from one of the Azure data center. So the x-axis and the y-axis are just absolute latency of the 2 concurrent requests. And as we can see, the concurrent requests are highly correlated. And here is another scatter plot from one of the S3 data centers. And still there, we can see that there are some requests that are correlated. So these 2 graphs show that requests have dependencies. And to capture these insights, our approach to estimate latency is to explicitly model the source of dependencies. For example, if concurrent requests hit the same replica, they're going to have same storage service latency. Or if concurrent requests take the same network path, they're going to have the same network latency. So after incorporating these insights, we can perform a more accurate latency estimation. So the graph here is the same example, but with a black line showing the latency estimated by CosTLO. As we can see, the black line almost accurately matches the measured line, which is the blue line, so the CosTLO can perform more accurate latency estimation. So now I have told you how does CosTLO work and how do we address some of the challenges. So next, let me show you some key results to show that our solution works. So we answer 3 questions in the evaluation. Can CosTLO meet SLOs? How useful are different forms of redundancy? And how much cost overhead does CosTLO incurs? And in this talk, I'll mainly focus on the first 2 questions. And the experiment setup is as follows. Application is deployed on Amazon AWS, and the CosTLO is deployed on S3 and Azure. We use 120 Platinum nodes as a client, and we use 1 week-long Wikipedia workload to compute cost. So the first result shows that CosTLO can indeed satisfy SLOs. So in this evaluation, we use CosTLO to bound we use CosTLO to bound a single request latency variance, and we set the SLO as the 99th percentile latency should be less than X milliseconds away from the median latency. The axis on this graph here is the latency difference between the 99th percentile latency and the median latency, and the y-axis is the CDF of Platinum nodes. So without CosTLO, more than 95% of Platinum nodes have latency information more than 50 milliseconds. So first, we set SLO equals to 50. So ideally, now the line should move to the left side of the green bar. And let's see how does CosTLO perform. So as we can see, more than 80% of Platinum nodes can satisfy 50 milliseconds SLO. And if we set SLO equals to 40, again, more than 80% of Platinum nodes can satisfy 40 milliseconds SLO. And the same applies when we set SLO equals to 30. So even though I'm not showing here, we can also configure CosTLO to satisfy application-specific SLOs. For example, for the application scenarios that I mentioned earlier in the talk, we can use CosTLO to bound the median web page downloading time and the median sync completion time. So the next result shows that it is indeed important to combine all forms of redundancies. And in this evaluation, we compare CosTLO against other configurations with limited forms of redundancy. And we set SLO as the get request tail latency inflation should be less than 40 milliseconds. So the graph here shows 2 aspects. On the y-axis, it shows that the y-axis shows the fraction of Platinum nodes that can satisfy SLO. If you remember from the previous slides, for CosTLO, more than 80% of Platinum nodes can satisfy SLO. And on the x-axis, it shows that for those Platinum nodes that can satisfy SLO, what is the cost inflation comparing with CosTLO? So each configuration will be a single point on this graph. So the more to the left and then the more to the top will be better. So when we use a single data center and a single copy of objects, only slightly over 20% of Platinum nodes can satisfy 40 milliseconds SLO. And also because of the poor ability of reducing tail latency, now the Platinum nodes also needs to issue lots of requests to fulfill client requests, which will incur, needs to issue lots of redundant requests, which will incur high cost. So if we want to reduce cost, we can add a relay VM. Adding relay VM can reduce data transfer costs, but it does not help improve tail latency performance. To improve tail latency performance, we can use multiple data centers. Now, around 70% of Platinum nodes can satisfy 40 milliseconds SLO. So if we want to further match the ability of satisfying SLO that CosTLO has, we need to add using multiple copies of objects per data center. But right now, CosTLO is still better in terms of cost because by using timeout and using redundancy probabilistically, CosTLO finds more opportunities to not issue redundant requests without violating the SLO. So this evaluation shows that it is indeed important to combine all forms of redundancy to reduce tail latency and the cost. So to conclude, in this talk, I present you CosTLO. CosTLO uses redundant requests to reduce latency variance, and it judiciously combines many forms of redundancy to satisfy SLOs with low additional cost. And our data sets are publicly available on this website, and thank you for your attention, and I'd like to take any questions now.
So as we saw in the C3 talk just a little bit ago, a lot of variance can come from contention on requests. And I'm reminded of TCP that in the face of contention, backs off. So what's different about the storage workload that makes it sense to double or even triple or quadruple the amount of traffic you're sending in order to deal with contention? Because obviously we wouldn't want to send TCP packets 4 times in the face of congestion just to make sure they get through.
Sorry, can you repeat your question? Because you were talking about TCP backup and what was the rest?
So in the face of congestion or
Okay.
contention for resources,
Okay.
TCP will back off in
Okay.
order to provide better performance. And here, you're not backing off. You're ramping up in the face of contention, which can only cause more contention. And so it's an arms race because if one person deploys CosTLO, another is going to be penalized for that. So why is storage different than TCP, that it makes sense to, in the face of congestion, congest the network more, whereas in the network it doesn't make sense to do that?
Yeah, thanks for the question. So you're asking about the network latency. So if this path is congested and the TCP will back off, so why this approach will help? Is that a question, right?
I'm asking why it makes sense that in the face of congestion, you should add more congestion to deal with the
Well,
congestion.
so the congestion will be per path basis. So the reason that the multiple requests will help because we're trying to leverage the path diversity. So if there are maybe some other passes that will have more, will be faster, and there will be less congestion. So that in that case, the redundant request will help.
But the system as a whole only has so much capacity, and now you're using it for redundant requests, ensuring that you have no more capacity to handle additional
But if
requests.
all the paths are congested, but in that case, yeah, redundant requests will actually make things worse and will not work. But we're actually leveraging the fact that load balancing on the internet, for example, some paths were congested, but for other paths it's not, and in that case, it would actually help reduce tail latency.
Okay, thank you.
Thank you.
I actually have a question. So I was wondering, as the cloud providers are not constant units, they change their policies. What does CosTLO do to adapt to changing cloud providers?
So CosTLO has a model. So the key components in CosTLO is estimate latency. So as long as so our model actually does not rely on individual cloud providers. So we have a general model that can model the latency distributions. And in that sense, if CosTLO change their underlying storage, then we can still apply the same mechanism to estimate latency. And in that case, we'll expect this approach will actually apply when the cloud provider actually changes their underlying.
Is that done on the fly, or is that something?
Yeah, it's on the fly. Yeah.
Other questions? Well, thank you very much.
Thank you.